Chapter 11 is on alkanes and cycloalkanes. We're going to go ahead and start with some definitions. First one is what a hydrocarbon is. And as the name implies, it's compounds that are made up of only carbon and hydrogen, as in our compound that is shown down here below, which is butane. So this has carbons and hydrogens. And this is what we call a saturated hydrocarbon. Saturated hydrocarbons contain only single bonds. So you can see between our carbons and hydrogens, we have all single bonds here. Versus an unsaturated hydrocarbon is one that contains double or triple bonds, like in this compound here. We have a double bond between two carbons, so this would be considered unsaturated versus saturated. Saturated means that we cannot add any more hydrogens. All of the carbons here have 4 single bonds. There's no place to add another one. So we consider that a saturated with hydrogens versus an unsaturated hydrocarbon, which we'll learn about in our next chapter, chapter 12, is you can actually break that double bond here and you could add to it so carbon has all single bonds, but that will be in our next chapter. So alkanes is a term we use to describe saturated hydrocarbons where we contain only single bonds. So in our compound here, we have single bonds between all of our carbon and hydrogens and between the carbons themselves. So an alkane is when the carbons are arranged in this open chain format versus a cycloalkane. If we look at the carbons, they're actually attached here in a ring. So that's the difference between a cycloalkane, the carbons are attached in a ring, and an alkane, they're attached in a chain format. Both of them are saturated with hydrogen. Some naturally occurring sources of alkanes include natural gas, which is made up primarily of methane, which is the fuel used in a stove at your house, unless of course you have an electric stove. It's also what's used in our Bunsen burners in the lab, and petroleum products. For example, here we have some oil coming out of the ground. It would be sent to a refinery and gone into a distillation column, which is this one here. And again, distillation is a technique that's used to separate mixtures based on different boiling points. So the ones with the lowest boiling points are going to be your heavier compounds, like asphalt would come from petroleum, versus maybe jet fuel, which has a much higher boiling point, and gasoline used in your car. So these are one way that you can get these different products is by distilling petroleum. So we're going to go ahead and review some structural and condensed structural formulas for alkanes. The first one we have here is methane. So again, the structural formula shows us all the bonds in our compound. So we have carbon with 4 single bonds to hydrogens. The condensed structural would just be showing us the number of atoms of each element. So in this case, it's the same as the molecular formula. Ethane, we have below, we've got 2 carbons, and then that is surrounded or saturated by all hydrogens. And then condensed, we would write CH3, CH3. The structural formula for propane is 3 carbons. And again, it's saturated with hydrogens. And we're showing every bond between every atom in a structural formula. And then the condensed, we'd write as CH3, CH2, CH3. And this is propane. That's the fuel that's in a barbecue. The next one we have is butane. Butane has 4 carbons. And it's saturated with hydrogens. And then the condensed structural formula, we would have CH3, CH2, CH2, CH3. Branching is a term we use to describe a branch of carbons that is connected to a straight chain of carbons. So for in this example below, we have a straight chain of 3 carbons, and this would be considered my branch, where it's coming off the center carbon, the CH3. You can also think of it maybe as a tree, and the trunk of my tree. would be my 3 carbons like this, and then I might have a branch coming out the side on my tree. We have a question here that can we put together another structural formula when we have 4 carbons and 10 hydrogens? Well, we could put together 4 carbons in a straight chain like what we've done before, and then again include all of our hydrogens by saturating my compound. So the question is, can we verify the rules of how many bonds does each carbon have? Well, each carbon has 4 single bonds. So when we look at these two different compounds, they actually have the same structural formula. They both have 4 carbons, and they both have 10 hydrogens. However, they're different compounds. So we're going to learn a new term for when you have compounds with the same molecular formula but different structures. Constitutional isomers are when we have compounds with the same molecular formula, but they have different structural formulas. So for example here, both of these compounds have 2 carbons, 6 hydrogens, and 1 oxygen. They have different structural formulas. So their molecular formula is the same, but they both have different structural formulas in the way that the atoms are rearranged. So for example, here we have a carbon, oxygen, and a hydrogen, and this we learned in the previous chapter makes an alcohol when we have that format, and this carbon here also has single bonds. This one down here, we have an oxygen between 2 carbons. This creates a functional group called an ether. So they have 2 different structural formulas, but the same molecular formula. So question is, are ethanol and dimethyl ether constitutional isomers? The answer would be yes. Are these 2 compounds constitutional isomers? The first thing you want to determine if you have a constitutional isomer is check their molecular formula if they're the same. So the one at the top, we have 8 carbons and we have a total of 18 hydrogens. This is called octane, which is one of the components in gasoline. The one below, if we check that one, it also has 8 carbons and 18 hydrogens. So they have the same molecular formula. The second thing to determine if you have a constitutional isomer is they have different structural formulas. So it's 2 parts in order to determine if you have a constitutional isomer. So we're going to look at their structures. The first one, we have 8 carbons in a straight chain. This one down here in our straight chain, we have a total of 5 carbons, and then we have some branching going on. So we have a branch here, and another branch there. So that means they have different structural formulas. So the answer for this one would be yes, they are constitutional isomers. Are these 6 compounds constitutional isomers? So again, first thing is let's look at the molecular formula for these compounds. So the first one, we have 6 carbons and we have 14 hydrogens. This one below, we have 6 carbons and 14 hydrogens. This one as well has 6 carbons and 14 hydrogens. And then the ones down below also have 6 carbons and 14 hydrogens. So we satisfy the first rule that they all have the same molecular formula. The next thing is to determine, do they have different structural formulas? Well, the one at the top, we have 6 in a straight chain. This one we have 5 in a straight chain, and we have a group or a branch coming off at the second carbon from the end. This one we have 4 in a straight chain, and then we have a branch coming off our second and third carbon. So those 3 are all different. Down here we have 4 in a chain, similar to this one, but here we have a branch at the top and the bottom on the same carbon, the second one from the end. So they are different. And then at the very bottom, we have 5 in a straight chain, which again is similar to this one here, but they are different because where the branch is connected is in the middle carbon. And we're going to be learning how to name compounds next. And one thing you can always do to check that they have different structural formulas if you're not sure would be to name them. So we're going to learn how to name these compounds.